We're now going to move on to a new topic in 3, 4, 5, 6, and that is ordinary differential equations. So many of the fundamental laws of physics, of mechanics, electromagnetism, chemical reactions, and a whole range of other things are framed in terms of spatial and temporal changes. For example, dx dt is equal to the velocity describes the motion of a fluid element in a velocity field. dv dt equals F on m describes the acceleration of a mass according to a force F. d squared x dt squared equals negative kx is the equation for a simple harmonic oscillator with a spring constant of k. Partial derivative of t with respect to t is equal to kappa d squared t dx squared is the heat equation, and it describes how the temperature varies as a function of time and space. dq dt is equal to negative u dq dx is the advection or convection equation which describes how something is advected and moved around by a velocity field u. These equations usually describe how one variable changes in time and or space as a function of time, space, and system variables. In all of these equations, we can see that derivatives appear on one and sometimes both sides of the equation. For that reason, these kinds of equations are called differential equations, and we're going to be looking at them extensively in the remainder of this unit. So let's get a little bit of terminology set down. You should probably all know this from Eng 1060, but it's worth clarifying. So let's take an example equation. dv dt is equal to g minus cd on m times v squared. This equation describes how a body falls in air due to gravity, that's the g term there, and as a consequence of drag, air drag, where cd there is the drag coefficient. And we looked at this in Eng 1060 in association with the bungee jumper. So, definitions. The dependent variable is the variable that is being differentiated, and here, in this equation, that's v. For a single equation, there is only one dependent variable. If you have a set of coupled equations, you can have more than one dependent variable. For things that we're going to do to begin with, we're only going to consider the case of one dependent variable. So it's the thing that can change. The independent variable, or variables, are the variables that are being differentiated with respect to. Here, that variable is t. In the heat equation, however, we can have derivatives with respect to t and x and maybe other things as well, so there are more than one independent variable. An ordinary differential equation is a differential equation that has only one independent variable. So this equation here is an ODE. A partial differential equation is a differential equation that has multiple independent variables. For example, the heat equation is written down here. So to begin with, we're going to consider ordinary differential equations. We're going to write the generic first-order differential equation as dy dt is equal to some function of t and y. So let's be really clear what we've written here, because students often get confused. Y is the solution of our equation. That's the thing that we're trying to find, and y varies as a function of time. That's why we've got this term here. We're saying that the derivative is non-zero, so y is a function of time. dy dt is the first derivative of the solution with respect to time. In other words, it's the slope of the solution. And dy dt is actually defined by this function on the right-hand side. And f, the function on the right-hand side, is a function that we know and is given. So y is the thing that we're trying to find. This equation is equivalent to saying the slope of our solution is some function of the solution and time. So let's have a look at an example. So the equation dy dt is equal to yt minus y cubed. That black line there is one solution of this equation. So what this is saying is that any value of t, and let's choose t is equal to 4, we have a value of the solution which is y. In this case, the value of y is approximately 1.72. At the point ty, in other words, at the point t is equal to 4, y is equal to 1.72, the slope of our solution is given by dy dt is equal to some function of t and y. And we've already specified the function here as being equal to yt minus y cubed. So the slope in this case then is equal to 1.72 times the time, which is 4, minus 1.72 cubed. I won't do that calculation. You can do that if you wish. So that's what this ODE is representing. Is this black line here the only solution to the ODE? Well, of course, the answer is no, it's not. To uniquely specify a solution to an ordinary differential equation, a first-order ordinary differential equation, we must specify an initial condition. And an initial condition looks something like y is equal to some value when t is equal to some other value. So, for example, that black line in the figure on the left there is the solution we find if y is equal to 0.001 when time is equal to 0. If we choose other initial conditions, we will get different solutions. So, for example, if we choose y is equal to negative 0.001 at time is equal to 0, we get the black dashed line. If we choose y is equal to 10 to the minus 4 when time is equal to 0, we get the blue line. Y is equal to negative 10 to the minus 4, we get the blue dashed line. If we choose y is equal to 0.1 or negative 0.1, we get the pink or the magenta lines. And various other solutions. Y is equal to 1, y is equal to 10 when time is equal to 0. So we get a whole range of different solutions depending on our initial condition. That's one thing you've got to be aware of. You can't find a solution to an ODE without an initial condition. These are often also called initial value problems because we need to have an initial value in order to find a solution. So that's all by way of introduction. We need to move on to try to figure out how we can solve ordinary differential equations.